Okay, so the next thing that we could do with this is what is called quantify the extent of connectivity in a graph. Okay. So for this analysis, you cannot use adjacency list. So you have to use a matrix kind of approach. Use the input as a matrix, and you will see soon why it is. So what we want to do here is to measure how connected is a graph. So what I mean by connected is, let us say given a graph like this, if you remove any edge in this graph, is the graph going to get disconnected? Or if you remove two edges in the graph, is the graph going to get disconnected? If you're going to remove one node from this graph, or the rest of the nodes going to be still connected? Okay, so again, we cannot but say particularly like I'll remove one edge and analyze the connectivity. I'll remove two edges and analyze connectivity. You can do that with breadth first search. You can remove an edge and see whether the graph is still connected. Of course, that's possible. But here what we want to do is to quantify the extent of connectivity, okay, in a graph. And the extent of connectivity in a graph that is already connected, in the sense that a given graph should be connected. Again, I mentioned in the breadth first search topic what I mean by connected graph. So a connected graph is a graph such that you can reach from one vertex to any other vertex. Okay, so it's not like this. So here this graph is not connected. It's a graph of say 7 vertices, but it's not a connected graph. We say this graph has two components. These 3 vertices form one component that are reachable to each other. These 4 vertices form another component that are reachable to each other. Okay. So again, the component is the largest set of vertices, such that if you add one more vertex to the set, that set of vertices is not connected. So you cannot say 5, 6, 7 form a component, even though they are reachable, connected to each other. You add one more vertex to the set, that also becomes a connected set of vertices. But if you add 1 to this 4 vertices, the set of vertices 1, 4, 5, 6, 7 is not connected because there is no edge between 1 to any other vertex here. So 4, 5, 6, 7 is the largest set of vertices that are connected to each other. So that's the definition of a component. So in a connected graph like this, all the vertices are in one component. Okay. So it is for such connected graphs we want to quantify the extent of connectivity. So look at these two graphs. Both the graphs are connected. Okay. But so if I remove vertex 1 and 5 from this graph, so if I remove vertex 1 and 5 from this graph, this graph is going to get disconnected. So think about, visualize the graph without vertex 1 and its edges. So these 2 edges will also be gone, and these 2 edges will also be gone, and these 3 edges will also be gone. So that means 4 will get isolated from 2, 3 and 6. So this graph 1 is going to get disconnected if you remove 1 and 5. Whereas if you remove 1 and 5 from this graph, all the other 4 vertices are still going to be connected. You're going to have 4 reachable to 2, and from there you can reach 2, 3, 6. So this is still going to be a connected graph. So this is what we want to kind of capture. If you randomly remove some nodes and edges, how likely is the graph going to get disconnected? How can we quantify that? Okay. So we have a measure called algebraic connectivity that captures this, and that is computed using the Laplacian matrix of a given graph. So first we need to look at what a Laplacian matrix is. Okay. So a Laplacian matrix can be computed from the adjacency matrix using this approach. So I say D minus A. D is the degree matrix, which I'll soon come to what it is, and A is the adjacency matrix. But let us look at this formulation, and from here we can know what is the degree matrix. So the Laplacian matrix is a square matrix like the adjacency matrix. So for any 2 vertices I and j, if if there's an edge between them, then the Laplacian matrix is going to have a -1 in its entry. So for example, so let me put the numbers here so that it's easy to visualize. 1, 2, 3, 4, 5. And let us put some numbers here. 1, oops. 1, 2. Okay, so 1 has an edge to 2, to 4 and 5. So the entries for 1, 2 will be -1. The entry for 1, 4 will be -1. For 1, 5 it is -1. In the adjacency matrix, these entries would have been +1, right? So in the Laplacian matrix you have -1. If there's an edge between two vertices, the corresponding entry in the Laplacian matrix will be a -1. And in the adjacency matrix would have been a +1. So that's why I indicate here -aij. So this aij is the entry for ij in the adjacency matrix of the graph. So if there's an edge between them, it would have been +1 there, and here you have -1 for those entries. If there's no edge between the two vertices I and j, like 1 and 3, they don't have an edge between them, and that entry will be a 0. And that is, you see, this is a general formulation. For any I not equal to j, the entry for the I and j in the Laplacian matrix Lij is -aij. What it means is, it's like -0. -0 is same as just telling 0. So that's why I did not put -0, it's just 0. Okay, so that's the rule. So if for any two vertices, different vertices I and j, two different vertices I and j, the entry is going to be a -1 if they have an edge between them. Like 1, 2 has an edge, so the entry is a -1. And 2, 3 has an edge, so the entry for 2, 3 is a -1. And 2, 5, they don't have an edge, so the entry is a 0. So if the two vertices don't have an edge, the entry for them is 0. So that's for two different vertices. Now what about the diagonal? The diagonal is going to correspond for I equal to j, it's the same vertex. Then you're going to simply have the degree of the vertex as the diagonal. Okay, so this is how you get the Laplacian matrix, and the this is a matrix calculation. So if you're given the degree matrix in the adjacency matrix, you can calculate the adjacency matrix by just doing the degree matrix minus the adjacency matrix. So the degree matrix is simply again a square matrix with one entries only in the diagonal. So you're going to have for vertex 1, 3, the other entries are all zeros. And for this 2, the degree of vertex 2 is 3. This graph here, its degree is 3, so you're going to have other entries as 0. So that's what a degree matrix looks like. For vertex 3 it is 2, that is its degree, and so on. So now you can already visualize why the Laplacian matrix is formulated like that. Okay, so this 0, 0, 5, 2. So now think about this. Such a degree matrix minus an adjacency matrix. So an adjacency matrix is going to have 0 in the diagonal. So it is 3 minus 0 is going to be 3. 0 minus 1. 1 in the adjacency matrix because 1 and 2 have an edge between them. So 0 minus 1 is -1. Then 0 minus 0. 1 and 3 don't have an edge, so the adjacency matrix entry is also going to be a 0. So 0 minus 0 is going to be 0. 1 and 4 have an edge, so it's going to be 0 minus 1. The adjacency matrix has a 1. So 0 minus 1 is -1. So that's this formula. So you can apply that formula and get the Laplacian matrix, or use the rule as I just mentioned. It's a square matrix with all the vertex entries, and it's going to be the degree in values of the vertices in the diagonal, and a -1 for two vertices that have an edge between them, and 0 for two vertices that don't have an edge between them. That's what is a Laplacian matrix. And once you get the Laplacian matrix of a given graph, what you need to do is again feed in this graph to your eigenvector matrix program. And you see here, you cannot get an adjacency list equivalent for a Laplacian matrix. You have to feed in type this matrix, like as I showed here, showed some time back. Let me type again. So how to type this? Type the vertex entries. These are the node IDs. Type exactly like what I have written there. So then 3, -1, 0, then -1, then -1. So make sure you have either a blank space or a tab. Anything should be fine. So you should feed in the adjacent Laplacian matrix like this. So then make sure that's the last line, there's no blank line. And so let us say so it's still a text file. So type some name and say it as a text file. So now open your eigenvector executable based on adjacency matrix. So this is based on the adjacency matrix. Double click on that jar file. So now load that text file that you just saved for the Laplacian matrix. Here. So that will compute again for the eigenvalues and the eigenvectors for based on the Laplacian matrix. Now you could see the first eigenvalue that is getting printed here is really close to 0. It's like -1.55 times 10 to the power -15. That's a very, very small number. So for all practical purposes, we can consider that to be 0. Okay, and the other eigenvalues are numbers like this: 1.586. I just round to 3 decimals. Then this is 3. This is 4.414, and this is like 5. Okay, so you could see you're going to get 5 eigenvalues for the Laplacian matrix here, because you're having 5 vertices. Now there are very important properties you need to capture here. Now there's going to be at least one 0 among the eigenvalues of a Laplacian matrix. Okay, that's one property, at least one 0. How many zeros you're going to have? Since I said at least one 0, how many zeros you're going to have among the eigenvalues of a Laplacian matrix? It depends on the number of components you have in the graph. Here you have only one component. All the vertices are reachable to each other, so the entire graph is one connected component. So you're going to have only one 0 among the eigenvalues of the Laplacian matrix. On the other hand, if you go through this process of determining Laplacian matrix of the 7 vertex graphs, this is a graph of 7 vertices here, but there are 2 components for this graph here. So if you compute the eigenvalues of the Laplacian matrix of this graph, so you can do that as a practice even during the break if you want to, you will get eigenvalues like this, and you can see there are 2 eigenvalues that are 0 among the 7 eigenvalues. So why there are 2 eigenvalues? Because there are 2 components for this graph. So this is a good application or thing that we can find out. So given a large graph of say several 100,000 vertices, it could have a lot of components. Okay, so instead of running breadth first search on each of those components and identifying how many components are there, we could simply build the Laplacian matrix of that entire graph and run through this program, compute the eigenvalues, and the number of zeros among the eigenvalues indicate the number of components in this graph. If you have only one zero, you're going to have at least one zero, so that's what I said in the beginning, there will be at least one zero among the eigenvalues. That's the number of zeros is the number of components. So if there's only one zero, then the whole graph is considered to be connected. So that is something also you can find out without running breadth first search. And again, the number of zeros correspond to the number of components. And another property among those eigenvalues of a Laplacian matrix is this: all the eigenvalues are going to be either 0 or positive. Okay, so you see there are no eigenvalues for this Laplacian matrix that is negative in nature. So for any graph you come up with a Laplacian matrix, the eigenvalues of a Laplacian matrix are always going to be 0 or positive. They are not going to be negative. Okay, that's an interesting property. Now another thing that you can also say is, if the graph is a complete graph, you see here, okay, the most important thing that we really want to talk about, the what do you call, the smallest positive non-zero eigenvalue is what really we are after. So in this case, among the eigenvalues, the smallest is 1.586, non-zero. The smallest non-zero eigenvalue among the eigenvalues is what is called the algebraic connectivity of this graph, and that's the measure of connectivity of that graph. Okay, so I would say, instead of telling the second smallest, the more appropriate definition is the smallest non-zero eigenvalue of the Laplacian matrix is a measure of the connectivity of the graph, and it's called the algebraic connectivity of that graph. Okay, now again you could get a feel of how much the connectivity is in this graph, right? So you see here, this is a graph of 5 vertices. So for a complete graph, you are going to get the algebraic connectivity to be the number of vertices. So that's the property. So the maximum algebraic connectivity for a graph of n vertices is n. So at most this could have been 5. Okay, so you get here 1.586. So you can now have a feel of the connectivity. So you can even take the ratio 1.586 divided by 5, but we don't take the ratio, just take the value, the eigenvalue as it is, and say that is algebraic connectivity of this graph. But you can have a feel of how large this could have been. This could have been 5 because the graph has 5 vertices. Instead of getting 5 as algebraic connectivity, I get 1.586. So that's a measure of how connected is the graph. How connected means, you see, you don't have that many edges among the vertices, but still the graph is connected. Okay, so the vertices are reachable to each other, but there are not that many edges. Okay, so you can use this approach to get the algebraic connectivity of any given graph. Okay, so what we'll do is we'll take a small break, and if you want to really try it out as a practice during this break, type the Laplacian matrix, run that through the matrix program for the eigenvalues, and try to get these numbers. See if you can get these numbers and try to interpret these numbers. So we'll come back after the break and run these two graphs and this one, and try to understand the numbers. Okay, and then we'll move on. So what time is it now? Okay, so let us meet back at 8 o'clock, and we'll try to continue with this. Okay, so if you have